Hey, thanks very much. I'd like to thank the organizers of this meeting. This is my first trip to ICTS and actually my first trip to India, and I've been enjoying it greatly, both the meeting and this very nice setting. I'm going to talk about physics and flat bands that occur in Moore array systems that we've heard about already from Ashvin, and I'll describe a few theoretical works that were inspired by these new types of systems, and at the end I'll also describe some new experiments done at Weizmann and our interpretation of these experiments that we think are telling us something interesting about the system. So just as a very brief background, because Ashvin already described the system in some depth. This is a new kind of strongly correlated system. Now there's a very nice quote that I heard quoted from Bhaskaran, who's here. So I think that really describes what's interesting about the system very nicely. So we heard a lot about twisted bilayer graphene, but this is actually one of many new systems of this class showing very rich behavior. So it's not just twisted bilayer graphene, there's also twisted bilayer and bilayer, trilayer graphene tuned by an electric field, twisted TMDs, and seems like the list is only growing. So what's so special about these systems? First of all, there's a very unusual situation if you're used to think about bulk correlated materials, that there's a very highly tunable band structure. So you can really tune the ratio U over W, which is not something you can usually do in a bulk material. There are multiple degrees of freedom, so spin and valley degrees of freedom, and they have a complex interplay between them. There's band topology that may be playing some interesting role, and its interplay with superconductivity and other strong correlation effects. And finally, something that will play a role at the end of this talk. So as we heard, this is a two-dimensional system, very, very dilute, very low density of electrons. So many of the usual probes that we're used to from bulk materials aren't available. So you can't do Newton scattering and so forth, all the first things that you do in a new correlated material. On the other hand, there are new probes that are actually not easily available in bulk materials that become available in this system. And an example of that is the electronic compressibility. And this is a thermodynamic quantity that you can measure readily with the right setup on this kind of system. And that can really tell you some interesting information about the nature of the correlated state in the system. Okay, so this is my plan. It's an ambitious plan, but I'll talk briefly about each topic just to give you a flavor. And the first topic, Debanjan has actually already talked about on Monday, superconductivity in flat bands. So what's the fate of this superconductor if you take the bandwidth to zero? So I'll be very brief. I'll just give you one slide on this. This is work of we have recently posted with Johannes Hoffmann, who's a postdoc at Weizmann, and Debanjan, who's here. Okay, so this is the kind of question that becomes relevant when you start thinking about these highly tunable systems. What happens if you have a superconductor? So there's some attractive interactions leading to pairing, and all the action is going on in this one active band, and the bandwidth of this band is highly tunable. So what happens, for instance, what happens if you turn on local attraction and you turn the ratio of the bandwidth to the attractive interaction to zero? You really go literally to the limit where this band becomes perfectly flat. Okay, so you might be worried on general grounds that what would happen is that TC would have to go to zero just because the phase stiffness would go to zero. So maybe electrons would form some sort of tightly bound pairs, but not condensed because the phase ordering temperature would go to zero at the same time. Okay, but there's an exception to this if the Wannier functions which are spanning these active bands are not localizable, so there's some overlap between the bands, then the superfluid stiffness actually doesn't have to vanish even in the limit when the bandwidth goes to zero. Okay, so then you get a very interesting situation where effectively, if U is small compared to the gap to the other band, the only relevant energy scale in the problem is the interaction. Therefore, the stiffness has to scale like the interaction, and you expect TC, if there is a TC, if the system is a superconductor, to scale as the interaction as well. Okay, this has been pointed out, but of course, this is intrinsically a strongly interacting limit. And as you go to this limit, you have to start worrying about other types of competing states to superconductivity, such as charge order, phase separation, and so forth. Okay, so we wanted an explicit model where we can really demonstrate this going on. Okay, and that can be solved in a controlled way. So we designed a band structure that has a very, very flat, even though not perfectly flat, a lower band. These two bands have Chern numbers. In our model, there are two spins. The Chern numbers of the two spins are opposite. Okay, so that overall the model has time reversal symmetry, and we partially fill this lower band. Okay, with some filling that we can tune. We turn on an attractive U, and then this model doesn't have a sign problem, and we can really solve it in a controlled way. Okay, and we've studied many properties of this model, but this is maybe the most striking one. The ground state indeed is a superconductor, and in the limit where this band becomes very, very flat, in the same units, this gap between the two bands is 4. Okay, so this is the bandwidth of the slowest band. Then TC actually scales linearly with U over a very broad range of parameters. Okay, we expect this to break down eventually for very small U, but we couldn't observe. We couldn't trace TC down to that to such small coupling strengths. Okay, so while TC indeed is set by effectively the only energy scale in this regime, which is just U, there's a particular coefficient, a numerical coefficient that we can compute. And if you increase the bandwidth of this lower band, it turns out that TC increases somewhat. Okay, so it is still favorable to have a bigger bandwidth, but then as you go to stronger interactions, the two TC curves approach each other. Okay, so this is sort of a new regime we think for superconductivity. We know now more about this regime, at least within this model. Okay, above TC, there's a very broad pseudo-gap regime, so the pairs form far above TC. There's a very close competition between superconductivity and electronic phase separation actually in this model, and now we understand how that happens and so forth. But okay, but this is just an advertisement for those of you who weren't here for the Bungeons talk on Monday. Okay, so now I'd like to talk about two other topics. Okay, the first is order parameter topology and dissipation in a fully spin polarized superconductor. And first, let me give the motivation that we had for studying this kind of system. Okay, so our motivation was actually a recent experiment done in a twisted bilayer on bilayer graphene. So these are two untwisted Bernal stacked graphene sheets, which are twisted relative to each other. Okay, so it's a variant on the twisted bilayer graphene system. And in this system, it turns out that you can control the bandwidth by applying a perpendicular electric field. So here the tuning parameters are not only the angle, but also this perpendicular electric field. And as a function of this field, you can get an isolated, very flat band. And much of the phenomenology is reminiscent of what you see in bilayer graphene. For instance, at half filling of this very flat band, you see a correlated induced insulator. And there's good evidence that this insulator is actually spin polarized. So the gap increases linearly with a parallel magnetic field, which is an indication of a spin ferromagnet. And as you change the carrier density slightly away from half filling, you see superconductivity. It's similar to what you see in twisted bilayer graphene. But the really striking thing that was pointed out in this paper by Philip Kim, where Ashwin was also involved, is that the onset of this superconducting state actually increases linearly with in-plane field at first. Okay, so TC, or T onset, goes like an absolute value of B in plane for small fields. Okay, so there's actually a cusp in TC, if you like, at B equals 0. This is very, very unusual. This is actually a signature of triplet superconductivity. Okay, so what happens is that, if you like, TC increases linearly for one spin flavor, decreases linearly for the other spin flavor, and the cross at B equals 0. This is very striking, okay, very, very unusual. Something like this has been observed in one of the phases of helium-3 superfluid, okay, but not in any solid-state system as far as I know. Okay, so this is very intriguing. This made us think of triplet superconductors. Okay, and I'd like to make a small digression and talk about the order parameter of a triplet superconductor. So this is a general way to write the order parameter. Okay, for triplet superconductor, so it's a vector order parameter. If you like, the vector is just the spin direction of the Cooper pair. And there are various ways this spin can arrange itself. So most generally, this order parameter dk, the so-called d vector, is a complex vector. Okay, so I can write it in terms of a real and imaginary part, two independent vectors. Both of them are functions of k. And for the purpose of this talk, I'll assume that the k dependence is not so important. It factorizes, okay, there's some function of k times this d vector. And I'll be focusing on a very special kind of a triplet superconductor. Okay, and this is actually important. So you can imagine a case where you're near a half metal, so the spins are in the nearby insulator, the spins are fully polarized. Now you change the carrier density a little bit. The state is still essentially fully spin polarized. So you only have one spin flavor, and that spin flavor condenses in the superconductor. Okay, so spin up in some basis is condensed, and spin down is not. So this is a fully spin polarized superconductor. It's a particular kind of triplet superconductor. In terms of this d vector, it would have the following description. So the magnitude of d1 and d2 would be equal, and they would be perpendicular to each other. Okay, and then it's really a two-line exercise to just insert this into this form and to convince yourself that this describes an up-up paired state, spin up and spin up electrons with k and minus k are paired, where up, of course, is arbitrary. Okay, and the direction of the spin, what's defined as up, is d1 cross d2. Okay, so this is the direction of the magnetic moment of the Cooper pair. It's a triplet spin 1 Cooper pair. S equals 1, M equals 1 in some direction. This is a convenient way to think about this order parameter space. Okay, so there are these two unit vectors. They're equal in magnitude. You can normalize them to unity. And d1 cross d2 is the direction of the magnetic moment of the Cooper pair. Okay, so these three vectors together form a triad. So the order parameter space is actually SO3. Okay, it's like a rotation in three dimensions in a orthogonal matrix. Okay, so that's a somewhat unusual order parameter space. And of course, the interesting case would be the case where we can neglect spin-orbit coupling, such that this order parameter can really point anywhere in a three-dimensional space. And that's an interesting case. And it's been studied in a different context some time ago. It turns out that there's no finite temperature transition actually in 2 dimensions because it's a continuous symmetry and you can't break it. Okay, so that's one interesting consequence of this state. But for the purposes of this talk, I'll assume that my system is finite. The temperature is small enough such that the correlation length is very long. Okay, so I don't have to worry about this fact. Okay, so what's interesting about this state is that gauge transformations and spin rotations get mixed in some interesting way. Okay, and that's really special to this kind of state. It doesn't happen in other triplet states that are not fully spin polarized. Okay, so the interesting thing about this state comes about when you start thinking about topological defects. So let me briefly describe that. Okay, so usually we're used to the fundamental topological defect in a superconductor being a vortex, and that's a point defect in two dimensions. And you know that the vorticity of a vortex is some integer. Okay, the phase of the vortex can wind n times. Now, in this case, it turns out that the corresponding homotopy group, so pi 1 of SO3, which is the order parameter space, is Z2. So here, the superconducting vortices are actually Z2. Okay, that means that you can't have vorticity 2 vortex. You can have a single vortex, but if you have 2 + 1 vortices, if you like, they can actually annihilate. They're topologically trivial. They're equivalent to the untwisted configuration. There's a pictorial way you can understand this. There's actually something called the Dirac belt trick. You can demonstrate this homotopy with a belt, okay? But I decided not to risk taking my belt off. So I'll just demonstrate this with a picture. Okay, so you can think about the space of SO3 as a ball. Okay, it's a full ball. The direction of the point in this ball is the axis of rotation of the SO3 matrix. The radius of this point, the distance from the origin, is the angle of rotations. And very importantly, you have to identify antipodal points on this on the surface of this ball at radius pi. Okay, this is because a rotation by pi around a certain axis is the same as a rotation by minus pi around the same axis. Okay, so if you consider a closed loop in this SO3 space, which goes like this, just a straight line from the South Pole to the North Pole, you can convince yourself that you can continuously deform this, this closed loop, okay, but just by gradually moving this starting and ending points, which are the same. Okay, these 2 points are the same. You just gradually slide this to this configuration. Okay, so this means that basically a vortex with a winding of +1 is equivalent to a vortex with winding of -1. But this configuration you can never deform into a point. So this is a non-trivial configuration. So this is sort of a pictorial way to demonstrate this fact. Okay, what does this mean for the superconductor? Okay, so this would have some consequences for current relaxation in such a spin polarized superconductor. Okay, so to study that, we wrote a free energy. So we assume that we're deep inside the superconducting state. We don't need to worry about fluctuations of the amplitude of the order parameter, only about its direction. So this is a nonlinear sigma model, if you like. Okay, and it turns out that there are only 2 terms in this elastic free energy that are allowed. One of them is just the gradient of this complex vector D mod squared. And the other one is related to gradients of D star cross D. D star cross D is thus just the direction of the magnetization of the Cooper pair. So if you like, this is the spin stiffness, the stiffness of the magnetization of the superconductor. And this part involves both the spin and the phase stiffness. So kappa m is really the difference between the phase and the spin stiffness. Okay, and there's a very nice way to parameterize such an order parameter in terms of a unitary matrix. Okay, so this is a nice parameterization that my postdoc Eyal found. Instead of using the D vector, which is a complex vector, you use this unitary matrix, and they're related in this way. The nice thing is that spin rotations are implemented by a unitary matrix multiplied from the left. Gauge transformations are implemented by multiplying by a matrix on the right. And that tells you also very easily how you describe a current carrying state. That's just this unitary matrix that depends on x. Okay, so this is a twist in the phase as a function of x. And now with the question we're interested in is if we start from this kind of configuration, how can the current relax? Okay, so usually in a superconductor, if you start from a configuration that's carrying a phase gradient that has a uniform phase twist, it's very hard to relax that because this is a topologically non-trivial configuration. The only way to relax this phase winding is to pass vortices, line vortices in 3D or point vortices in 2D that would unwind this phase. Okay, point defects. Here it's actually possible to unwind this phase twist even without point defects because of the fact that every 2 phase windings are actually trivial. So here's the way to see it. So this is a configuration of this unitary matrix U that depends on x and on a parameter tau that goes from 0 to 1. And at tau equals 0, this configuration carries n of these phase twists, and at tau equals 1, it carries n minus 2. Okay, so overall, this unwinds 2 of these phase twists. Okay, this is a very convenient configuration that Eyal wrote. This is what it looks like. Okay, so this is tau, this is x. Here, the green arrow is the direction of the magnetization. The phase is twisting, and you basically go through intermediate configurations where you twist both the phase and the direction of magnetization. The green arrow, the magnetization, actually forms a half a skyrmion over this range. Okay, and at the end, you've unwound 2 phase twists. So at tau equals 1, the end of this path, the magnetization is again uniform. okay, in the opposite direction, and the phase is also uniform. Okay, you started here from a winding of 2. What does this mean for dissipation of currents? Okay, so we start from a configuration that's carrying a supercurrent, the phase is winding, and now we're going to assume that there is some mechanism to dissipate spin. Okay, that's important. If spin was perfectly conserved, this configuration would be as stable as in the usual superconductor. Okay, so but we assume that because of residual small spin orbit coupling, or because of some kind of magnetic impurity, some sort of spin bath, or just the coupling to the leads, the system can actually dissipate spin over time. Okay, and that's going to be important for this current relaxation mechanism. If that's possible, we can study the energy landscape as a function of tau, this path parameter. Okay, so we start from this configuration that has a phase twist, and we ask, is there an energy barrier along this path? Okay, so what's the free energy as a function of this path? We know that at the end we can decrease the energy. It turns out that under certain conditions there could be an energy barrier on the way. Okay, and this is the maximum. This is how the maximum energy barrier scales as a function of these two stiffness parameters, kappa m and kappa d. Okay, so kappa d is if you like, it has a component both in the phase and in the spin stiffness. Kappa m is the excess spin stiffness, basically the difference between the two. Okay, and if kappa m is small, if the two stiffnesses are equal, for instance, there's no barrier to unwind two phase windings. Okay, so the only stable configuration is a single winding, which is topologically stable. If kappa m is large, you'll get a finite barrier unless the winding exceeds some finite value. So there's some threshold. What this means, now the threshold is a finite number of windings. Okay, and it's a finite number independent of the system size. So that essentially means that there's a critical current to the system which is proportional to 1 over system, 1 over the system size. Okay, so this is quite unusual. Usually in a superconductor, there's a critical current density. Here, the critical current density actually goes to 0 in the thermodynamic limit. So here, superconductivity is really a mesoscopic phenomenon. Okay, this is what this is telling you. Yes. Could I define M? Yeah, so n is the number of phase windings in the original configuration. Okay. All right. So yeah, this is what I plan to say about this, and I have 7 minutes. Yeah. Okay. So I'll be brief. Let me describe some experiments done at Weizmann, and our interpretation of these experiments. These experiments were led by two very brilliant students, Uri and Asaf in Shachar Ilani's group. And this work has been done in collaboration with theorists at Weizmann and elsewhere, in particular Adi, who's here, and with Pablo Jerry Herrero's group at MIT, who provided both samples and insights. Okay, and the question here is this. So as we heard, a twisted bilayer graphene close to the magic angle is tuned to this point where the bandwidth is very small. The bandwidth is most probably of the same order or maybe smaller than the interaction strength, both of the order of 20 to 30 millielectron volts. And this is sort of the, if you like, this is the high energy scale in the problem. And empirically, we know that at low energy scales, maybe between 0.1 and 1 millielectron volts, these interesting correlated states emerge. So either Mott-like correlated insulators, superconductors, and so forth. Okay, but the question that Ashwin already posed actually a couple of days ago is how should we think about the intermediate scales here? Should we think about a doped Mott insulator is the big energy scale with a big energy scale of U and everything is local? Or should we think about this more like a quantum Hall ferromagnet or something else? Okay, so what's the nature of the state in this intermediate energy window? Sorry? Yeah, so this is not a pocket, it's two bands that are touching at some Dirac points. Okay, so yeah, that's it turns out that this is what band calculations for the system give. Right? Okay, so the way Shachal's group addresses this is by compressibility measurement. So be very brief. Okay, so what the quantity they measure is a d mu dn, derivative of the chemical potential with respect to density. Okay, more specifically, what they do. Okay, so they measure basically the derivative of the total energy of the system with respect to charge. This is like inverse capacitance. Okay, so there's the system, which is close to a backgate. You can change the density using the backgate. And Q is just the charge on the backgate, which is equal to minus the charge in the system. And you can really vary this thing and measure this quantity. Now, it turns out that this quantity mostly is just the usual 1 over capacitance of a geometric capacitor. Okay, if this was a perfect metal, this would be boring, just A over D, the area divided by the distance. So you want to subtract 1 over the geometric capacitance, which is what you would get if this was a perfect metal. This really gives you the intrinsic property of the system. This is like subtracting 2 big numbers to get a small number. Okay, and this may be hard to do in practice because if there's a small error bar on each one of these 2 quantities, you get a big error bar on the result. Okay, but there's a beautiful trick to actually do this. What you do is you don't quite do this subtraction. You measure how much electric field is a third plate, and you measure how much electric field is penetrating through. If the system is not a perfect metal, it's not perfectly screening the field. And that's this trick by Jim Eisenstein. And this is actually what Shachal's group does. Okay, now in addition, what they do is scanning. So their third plate, which is the probe where you measure the electric field to measure compressibility, is actually on a tip which you can scan around, okay, with a spatial resolution of a few hundred nanometers. Okay, and this actually turns out to be crucial for this system. Turns out that the system is very inhomogeneous, and it's really important to look locally in real space. Okay, so they get actually different results, different twist angles, and therefore also different results depending on where they look. Okay, so what they really measure is d mu dn, this a so-called quantum capacitance, the electronic compressibility, as a function of gate voltage, density, and position. Okay? Yeah, so they can't tell on the 100 nanometer scale because that's the spatial resolution, but on micron scale, it varies. There are patches, yeah, okay. Okay, so this is what a scan looks like. Okay, so this is in a particular point in the sample. This is the mu dn as a function of density. And you see here 3 prominent, so the black here is d mu dn. The purple is the integral. This is mu as a function of n, chemical potential as a function of n. Okay, and you see here 3 prominent features. I'll start from these 2 sharp peaks. Okay, 2 delta function-like peaks. This is what you expect in a gap. If you think about the gap, so a mu as a function of n at the gap jumps when you change density across a gap. So the derivative is a delta function. Okay, so these 2 peaks are just the band gap, the band gaps between these 2 middle flat bands and the other bands. Okay, and this actually allows them to identify the angle. So from this, they know the density that corresponds to filling plus or minus 4 electrons in the flat bands. Okay, now at the charge neutrality point right in the middle, you see this peak, which is broader. It's not quite a delta function. And the way they interpret this is in terms of a Dirac dispersion. So these 2 bands are expected to touch in Dirac points. And if you had the Dirac point, the mu dn should diverge. Okay, so a Dirac point is a reduction of the density of states, so the mu dn increases, and it's supposed to diverge like 1 over square root of n. Okay, so it's supposed to diverge on both sides. In different parts of the sample, this looks more or less like 1 over square root of n, but they interpret this as some sort of Dirac-like feature. Okay, so this is overall consistent with what you expect from the band structure. But when you look at more details, interesting features start to appear. Okay? And in particular, interesting features appear at a non-zero integer or close to non-zero integer fillings. Okay? So this is what happens close to +2. This is adding 2 electrons per Moiré unit cell. And you see what happens. So the red is 4 Kelvin. You start seeing already this, this kind of feature. And it becomes more pronounced when you cool it down to 50 milli-K. So as you approach a filling of 2 electrons per Mole, what happens, okay, so I'll take 3 more minutes. What? It's the same data. Yeah, it's just a blow up. Yeah. Okay. So what happens is you see this very asymmetric feature. Okay. So the inverse. This is the inverse compressibility. It first drops, okay, and then it rises sharply, and then decreases very gradually on the other side. Okay. So now let me stress. Okay. So this is really not a gap. What you're seeing here is really not a gap. A gap should be a delta function, a symmetric delta function like peak, which is what you see here. In particular, this drop is almost 0. Okay. I'll show you later in the next slide. Sometimes it goes negative. Okay, so this is like this is a very large compressibility. It's not what you expect from a gap. It's kind of the opposite. This is a sharp increase, but it doesn't look like a gap. Okay, so it looks more like a copy of what you see here, close to the charge neutrality point. And this is actually seen in many parts of the sample. It becomes more pronounced when you approach magic angle. And some of these features also become more pronounced when you apply an in-plane magnetic field. Okay, I won't go into details. I'll just describe very briefly our interpretation of this. Okay, so we start from four flavors, okay, two spins, 2 valleys. At charge neutrality, they're all close to the Dirac point. We see evidence for. Then we start filling carriers into the system, say electrons. And at first, they all start filling together. But at some point, due to exchange, like a ferromagnet, you actually favor polarization, so you fill, rather than filling all of them together to save exchange energy, you want to polarize, so you want to fill one of the flavors completely, either spin, valley, or some combination, depending on details that we haven't considered at this level of the modeling. Okay, and the other flavors at this point would return to the charge neutrality point. So what you'll get is a recurrence of the Dirac dispersion close to filling nu equals 1. And then you start filling these 3 again, and when you approach 2, they would break the symmetry again and polarize 2. Now choose 2 flavors, fill them, and the other 2 would set back to the Dirac point, and so forth. And this is our description of this trace in the inverse compressibility. Okay, I won't go into details. They're very, very simple mean field model with a local repulsive interaction that shows very similar behavior. Okay, so this is the inverse compressibility from this model. Okay, it shows some interesting sequence of transitions as you approach the integers, which you can ask me about. Okay, and in particular, you see these dips. These dips are signatures of first order transitions, and these are actually phase mixture regions within this model, at least. Okay, so I won't go into, I'll skip these details and conclude. Okay, so I hope I convey that these are very, very interesting new types of correlated systems. I talked about superconductivity in flat bands, fully polarized triplet superconductors, and new measurements of the electronic compressibility that seem to indicate spin and valley symmetry breaking. Okay, thank you very much.
Thank you, Erez. Questions?
In the last part, I just wanted to confirm that the data showed peak at nu equals 4, which
Yes.
is correspond to just a gap.
Yes, yeah.
That's consistent with you have a 4 Dirac bond to start with.
Yes, yeah. So that's
Once you reach nu equals
consistent.
4,
Yeah, yes,
or the Dirac cone surface.
yes.
This sample doesn't show an insulating phase at nuclear 2. If you did.
Right. So this sample never actually showed an insulating gap at t equals 2. Yeah. So the maximum angle here. So the angle is varying. The maximum angle here is 1.07. So it's kind of approaching the magic angle. There's a new sample that mostly also doesn't show a gap at nu equals 2. There are parts of the sample that I'm not allowed to talk about. Right. Tell you, I may have to kill you. Right. But yeah, but the new sample is much bigger, and mostly it's very consistent with this.
This W over U limit, I mean, singular, right? If you take W equals 0, you should get 0. So what's the small
Yeah.
energy scale that?
Yeah, right. So interestingly enough, it turns out that that's right. If you take W equals 0, no, sorry. Let me rewind. W equals 0 should be finite. The limit should be finite. So that's the special thing about this problem. Okay, TC actually doesn't vanish even in the limit W goes to 0. Okay, and you can ask why? How is that possible?
How is that possible?
A way maybe to think about it is this way, right? So it's a completely flat band, but it's an untrivial band. So if we put a single particle in this band, because of interference, it doesn't disperse at all. It remains localized. But if there's an attractive interaction, if you put two particles together, they form a bound state, and this bosonic bound state disperses. Okay, this bosonic bound state now doesn't have the same interference as a single particle. So there is phase stiffness, even in the limit W goes to 0. Okay?
Won't form a Wigner crystal or any?
Not necessarily. Not necessarily. Here it doesn't. Okay, here we believe it doesn't.
So, just like you said that near the even integer filling, so there are the emergence of the Dirac-like behavior is there.
Yeah.
So,
So let me just stress that indeed near the integer fillings, the Dirac behavior reemerges, but only at one side. Okay, so for instance, on the electrodoped side, it's at 1+ and 2+.
Yeah.
Okay, but not on the other side, and that's actually interesting.
and numerically it goes as like 1 by square root of n.
No, it doesn't quite fit nicely. Okay, so you should wherever I say Dirac, you should really replace it with Dirac-like. Okay, so some reduced density of states that kind of qualitative looks like what you expect for Dirac, but maybe it doesn't. The density of states doesn't quite go linearly all the way to 0. It goes to some constant.
Please, TC over delta, delta over TC, and which goes to 0? Ratio the same as in BCS theory, or?
TC over delta. We haven't measured delta. Yeah, we can and should do that, but most probably it would not be BCS. It would be very, very different, but it would be a number of order 1.
Have a wave function, like BCS type wave function?
So there's a particular limit which is interesting, where the BCS wave function essentially becomes exact for this model. In the same limit, TC is 0, because this is a limit where the model actually has a low energy SU2 symmetry that relates spin and charge, superconductivity and charge, and it's 2D, so TC is 0. Okay, but it's the breaking of this SU2 that allows us to observe a finite TC. Yes.
So this is different from, I mean, what, for example, Ashwin was saying yesterday. So other samples is actually insulated in the charge neutrality.
Yeah. So
of course, there's a sample dependence, but
yeah. So there's some sample dependence there that at charge neutrality that people don't quite understand. So samples by the MIT group, by Columbia group, Santa Barbara actually don't show a gap at charge neutrality. They show a peak in the resistivity, but it's not an insulator. Okay, both in terms of the value and the temperature dependence. On the other hand, the samples from the Barcelona group do see a gap. Okay, they claim to see activated behavior and even extract the value of the gap, and it's quite big. Okay, now this might have to do with alignment with the HBN. It's known, so the experiments from Stanford and Santa Barbara aligned the twisted bilayer with the HBN, and then it's understood that you should see a gap just because of the single particle band structure at charge neutrality. But it's not quite clear what's the difference between the other samples. Okay, now at 2, people do see a gap, and here for some reason in the compressibility, so people see a gap in transport, but here in the thermodynamics, you actually don't see a gap. And also in STM, in single particle spectral function, you don't quite see a gap at 2, okay, or any of the integers actually. No. Yeah, so we don't expect a very strong signature of superconductivity in compressibility. So it's not clear that you should expect something, yeah.
Move on then. We thank Erez once more for talk.